I was really grateful to get to attend different talks yesterday. Learned a lot about what's going on in the conference here. My background is working in AI, machine learning. I'll give a little bit of overview of some of that, but I definitely led a lot of data teams in industry, and I've been involved in large open source projects in the space of data science. I'm at O'Reilly where we do have a lot of audio and video content. We historically have published books for the last 40 years, but also done a lot of instructional videos and a lot of conferences. And one of the things is that we come out of a conference with maybe a couple hundred hours post-edit of high-quality video. And people viewing that content subsequently, maybe even years later, it's a large revenue stream. And so managing that video, making it available for people as learning materials is important, because part of the thesis of O'Reilly is really about what I would call peer teaching. Over the past 40 years, since Tim O'Reilly and Dale Doherty were classics majors back at Harvard, what they've found is they could go into technical communities and find out who are the people who are really innovating and take them and put them up on stage as peer teachers. So my team back at O'Reilly is involved in using some of these technologies. I want to show it's not the kind of thing that's going to be immediately available in products today, but I think that there's perhaps an interesting generation of product advances coming up. I can give a little bit of a preview. The other thing about O'Reilly is that we have had, like I say, about a 40-year span of trying to look ahead and forecast what are the emerging trends in technology, what's coming up, and what are the issues driving it, who are the people really involved. So back in the day, the first one of those was something called Unix. And so Tim O'Reilly was out there saying, hey, there's this new operating system called Unix. You should really pay attention. And got a lot of pushback, but eventually, Unix became a thing, Linux, et cetera, afterwards. And the next one was something called World Wide Web. They got out there early on and were saying, this is coming up. You might want to pay attention. And then after that, they became one of the first e-commerce firms. And they said, gosh, people are going to transact online. And I remember that part. And a lot of business folks at the time were saying, no, this will never happen. So we've had a long history of kind of trying to see where the trends are. A lot of my work is, again, more in the AI side, so I've been tracking that space pretty closely. And what I want to present today is one of the themes that we see emerging in the AI sector, which I think will have a lot of bearing here, is about, as mentioned on the title there, active learning. Active learning means a few different things, but here it's a form of machine learning. It's also called human in the loop. And so it does present a way to blend the best that we can find out of machine learning, along with where do the people who have the expertise and the intelligence, where do they also have their input into the product. The other thing that I will talk about is Ontology, which is another name for what's commonly called knowledge graph. I have a lot of background doing that, going back into grad school. And so this is an aspect of AI that probably doesn't get as much airtime, but it's also bubbling up. And being able to blend together the active learning side with the knowledge graph side is a very powerful thing when you're trying to understand natural language. And I think it has a lot of applications here in the very near future. So a little bit of background. I came through this in a strange way. I just want to give a few vignettes of some of the things that I'd worked on, and also what we'd seen at the time with respect to natural language and AI emerging. So rolling the clock back into the early 80s, I had the strange idea to study artificial intelligence in grad school. And unfortunately, my timing was very off. It was a little bit too early to be doing that. But we had some interesting projects. I worked in IBM Research and NASA. And then the AI winter hit, as was mentioned yesterday a couple of times. So definitely lived through that. The upshot was I went to go do work in neural networks. And so I spent about 7 years in R&D on neural networks. And again, it was very early, but we started to have some interesting applications. I was on a project that was kind of a precursor for smartphones. It was out of Motorola, and we were doing Asian handwriting recognition on phones, embedded in phones. And we were also building custom hardware for neural networks because we recognized that that was the bottleneck. So we were limited by what the compute hardware could do. But again, it was pretty interesting to see neural networks, like I say, back in the 80s, going into the 90s. Rolling the clock up about a decade, World Wide Web was coming out, and we had a strange notion to launch an online bookstore. And that was in December of 1992. So we did an online bookstore, got into e-commerce, and partway through there, we had some chat rooms. So one of the things we did was to leverage the chat rooms and put in chatbots for customer support. So by 1995, we were doing customer support with natural language. And one of the strange things there is we noticed that people would spend inordinate amounts of time playing with the bots. So we figured, okay, let's leverage that. The approach that we took was actually the bots would have a lot of humor that we tried to build in. There were some comedy routines that could be triggered if they got stuck. And at times, we would have our retail staff, if they were seeing a conversation that was interesting, they had the option to take over a conversation, take the bot's place. So you would see these transcripts that were just hair-raising, where somebody was playing with a bot, and then suddenly they realized, hey, maybe this isn't a bot I'm talking to. So it led to a lot of humorous scenarios. There's a gentleman named Robbie Garner that I worked with on that project, and Robbie went into competition with bots. He's been doing this for about 30 years. There's an international competition, a Turing test, called the Loebner Prize that went on for a long time, and Robbie competed a lot in that. We actually took that onto live television for BBC in 1998. There was a popular show in the UK called Tomorrow's World, and we did, it was televised to 20 million people. We had a live Turing test where people could log in to the BBC site and try to see if they thought the person they were talking to was a bot or a human. We were able to score 17% at the time. Now, with a Turing test, the possible score is 50%. So we're like a third of the way there, which is a pretty good score. It was a lot of interesting work. Robbie is now working on Android bots, or working with people doing Android robots and adding natural language to them. And then rolling the clock up another decade, some of the same people involved. We were noticing that social media was coming up, and we were also seeing a lot of interest in internet-based virtual reality. So there was a generation of that. How many people here ever saw Second Life? Anybody work with that? Okay, great. So that was coming out. Facebook was relatively new. Twitter was new. And we had a company that was involved in parsing dialogue out of social media and trying to use that to train responses that we could put into avatars in these virtual worlds. So you could have basically an avatar in a virtual reality that was a bit like an answering machine or more of like a customer service chatbot today. We made some headway there, although I don't think Second Life really lasted all that long. But it was interesting because we could use computer, if you will, data structures or data formats to represent film scripts and use that to represent the dialogue that we were seeing and work on parsing it with NLP. That company was one of the first customers for Amazon AWS, and so we got to work really early on with them. One of the things that we found was we had some bottlenecks, and we started using a new project called Apache Hadoop. How many people here have ever worked with Hadoop or Spark? Okay, great. So this was back in 2006. We started working with Hadoop, and we ran into some problems and did a little bit of work. And this company, based on Second Life, didn't go very far, but it got acqui-hired by an ad firm. They were very interested in being able to do NLP off of social media. And with that ad firm, we became the largest Hadoop instance on AWS and worked very closely with them. There's now a service that used that for a case study. It's called Elastic MapReduce. So I got to see at 3 different vignettes here some pretty interesting applications of working with natural language. And at each point, the thing that was holding us back was a lot of the compute power. We had very interesting software and algorithms to use. a lot more that was predicted by the math that we could do, but we were really held back by the compute power. But cloud computing was an interesting thing. It really kind of broke that open. And for me, it showed that there was a lot of room for leveraging graphs. And I mean that in terms of some sort of graph structure, applying graph algorithms. Even for people who have degrees in mathematics, graph algorithms are a little scary, but they're very useful when it comes to NLP, and that's part of what I want to show. Okay, so let me give a little big picture here about where we see AI. We do work with most of the leading teams in the world who are doing research in AI. We work with them to put them up on stage, but we also talk with them privately. We get to compare notes behind the scenes between them and see where are the interesting startups, what are the interesting research projects, what are the enterprise use cases where the pain points are. So I want to try to summarize that. And first off, I'll definitely point toward one of my colleagues and close friends, Ben Lorica. He's our chief scientist, used to be a UC professor in financial engineering and was a quant for Wall Street firms. Ben does a summary every quarter, basically a landscape of what's going on in machine learning and AI. And every day he's out there talking with all the leading people trying to figure out what's bubbling up. So I definitely recommend Ben's podcast and his articles because he really is tracking where is this going. And there's a pretty good history on this methodology for tracking emerging tech. And so what we've seen, I think probably the best summary of it so far, this will be paraphrasing Andrew Ng, a well-known Stanford professor, or formerly Stanford professor. With AI, there were really three factors that came together that enabled commercialization. And so the first thing is big data, and the next is big compute, and the third is big models. And to give a little bit of background, big data really started out in Q3 of 1997. There were 4 teams that were struggling with the same problem. It was what would become Google, Yahoo, eBay, and Amazon was already going. And so 4 teams, and they've all documented it. Greg Linden at Amazon, Randy Shoup from eBay, on and on. They've documented what they were thinking and how they approached it. Basically, they came to the conclusion that e-commerce was about ready to really take off, but at the time, they were running on like single servers. So eBay at the time in '97 was 4 servers, all of eBay. So what they realized in Q3 was they had to get ready for holiday shopping. And 4 teams independently took and distributed their workloads. They got away from having bigger and bigger Oracle licenses, and they distributed their workloads onto more open source approaches, Linux, on commodity servers. And they could run basically private clouds. And they took their workloads and parallelized them to spread them across a lot of little servers. And the phenomena that happened was, well, A, those 4 companies were in place for Q4 of 1997, which was the first real big success for e-commerce. But then what they saw subsequently was that when you have a bunch of servers running all these transactions in e-commerce, you get a lot of log files. And again, these companies and others that started joining them, they started aggregating the log files, bringing them back together, and then running machine learning on the aggregate. And from that, you could produce what became called data products. You could have classifiers, indexing, recommendation systems. That all would feed back into the web apps that were generating the data in the first place. So what you did was you could see a kind of virtuous cycle emerging, a kind of flywheel effect, where the e-commerce transactions created data, you aggregated it, used machine learning to improve the smarts, the intelligence in the e-commerce apps. And that allowed these companies to become giant, but it also set the mode for others to follow. And it was really the origins of big data. One of the things that we see with this kind of analysis is how many people have ever run across like J-curve forecasting? I don't know if that's an obscure term, but basically for these kind of technologies, we see a window of about 10 to 14 years from the point where they're invented to the point where they become commoditized. And the midpoint right in between there is where the early adopters really come in a serious way. You see an inflection point generally. So 1997 for big data, that's when it started. Roll the clock out about 12 years, you get out to 2009. Am I doing my math correctly? And what you find is that's when big data first started coming into parlance in the industry. It was about 2009. Data science and big data hit about then. That's when we launched the Strata Data Conference about big data. And then you roll the clock out further, you get out to about 2017, and big data, you see airport advertisement about it, right? So it's really commoditized by now. The other factor is big compute. That really started in the early aughts. How many people use cloud services? Amazon, Google, Microsoft? It's a lot more hands these days. Back in 2006 or even into like 2010, it was still kind of iffy. What happened there was in the early aughts, VMware and Cambridge and some others came out with software to do virtualization. So you could have your computer running, but then you could run a smaller virtual version of a computer inside of it and partition your resources. And so that was, let's see, I think hypervisor was like 2002, 2001. Intel did hardware for virtualization in about 2003, 2004. In 2006, Amazon launched AWS. And the other thing that's not mentioned a lot is in 2006, Google contributed a library to Linux. It's called C groups. It's kind of obscure, but it allowed for virtualization. And they contributed it open source. It was in the 2.6 release of Linux, like I say, 12 years ago. But what that enabled was a bunch of other software. So Apache Mesos, Kubernetes, Docker. How many people here have run across Docker or used containers? Okay, more. So that all came out of Google making a contribution to Linux. And again, that all started in the early mid-aughts. And you can see now that, again, about 12 years later, this is really becoming commodified. And that's moving forward. I'll talk more, but that space of hardware in the cloud is really changing rapidly, and it's a big driver. The third part here is about big models. And so neural networks are interesting. They go back into the 40s with McCullough and Pitts at MIT. But again, it took a long time before we really had enough compute power for neural networks to take off. And so in 2006, Jeff Hinton published a paper about having layers and layers of neural networks stacked on top of each other using a thing called an autoencoder in between every layer. And they could do magic with it. They just didn't have the right data for that to really show it off. It took them 7 years to find the right data set. But in 2013, they published a paper that took ImageNet data, a bunch of images, and ran them through deep neural network structures. And one of the grad students was Alex. He has a Russian name, and I apologize, I can't pronounce it. But he put some code on GitHub called AlexNet. And it was basically a way of taking ImageNet, running it through a deep neural network. And interestingly, he also added the option that you could use GPUs, graphical processing units. You could use GPUs to make the thing run much, much faster. And he made that all open source on GitHub. And from 2013, that just took off. I have a friend here in DC who had the first DARPA contract for defense-related use of deep learning. And it was a two-person company, and they did the challenge at DARPA for like F-16 fighters for incoming target, whatever identification. They were able to apply deep learning on that data set with all these huge defense contractors competing, and they were able to beat out the closest competition by 25x. And we've seen this down the line, that deep learning has some really amazing consequences. And so that all started in 2012. It'll take about 12 years to be commodified. That gets us into the mid-2020s. So we're seeing interesting things with the big models right now. Okay, there's a little bit of a history lesson. Let me jump into something a bit more. I'm going to zoom past this part. I will say, hopefully I'm kind of speaking to the choir here, but human parity is, if I have to give a definition for AI, I like to look at examples of human parity. And here's a great report out of Microsoft in 2006 where they were able to get the error rates on speech-to-text to beat the benchmarks for human transcription. And it's really interesting because you find this at an error rate of about 5%. We see that machine learning models tend to fall apart after you get into the 90s, and it's that last 5% that's really difficult, really expensive. We also see that with humans, there's typically kind of that same 95 to 5 ratio of whether you're working in speech or other domains. Beyond 95% accuracy, you get a lot of diminishing returns. And part of that is because humans, beyond that 95% level, tend to use judgment. There's a lot of edge cases, a lot of judgment calls. So that 5% is where we're working with the human in the loop part. And let me get to the chase here. So for O'Reilly, we have a lot of media, a lot of interesting experts who are weighing in on new topics. If we have content that's already text, we can parse that with NLP. If we have images that have labels on them, like somebody making a talk and they've got slides, we can do interesting work with labeled images. All of that assumes that there's some kind of structure inside the data. So we assume that a text document is going to have certain themes, certain key phrases in it, and there'll be references within that text. People keep mentioning the important parts. So we assume there's some kind of structure. I have a little graph to depict that. And as an example, this here is, we have an instructional video about Docker by Andrew Baker. It's a popular video. This is a project where we've been partnering with Google with some of their AI capabilities. So up in the top left corner, we'd taken we pulled an MPEG off of this video and provided an audio segment to Google. They come back with a raw transcript that's up in the left. And it's a pretty good transcript out of this intro part of the video. It also has a confidence value of about 97%. So we're able to take that and notice that the transcripts coming back from the APIs, they lack punctuation. So we have some machine learning models to put punctuation back in. But once we're able to get a transcription, then we can run through in the top right-hand side the parsing. And for this, we're using Spacy. Anybody else here working with Spacy? Excellent. So it's in Python. It's really the best library currently for NLP. So we parse a text, and we find out for each item, for each word, what is its part of speech, and what is the root word. And then we're able to use another project called PyTextRank. It's a way of using graph algorithms for natural language understanding. So once we've got a parsed sentence, then we can build a graph out of it and run the algorithms. In the bottom right-hand side, you can see key phrases. Not just all the phrases, but what are the most highly ranked phrases? And the reason for these to bubble up is that they're the ones that are referenced by the rest of the text the most often. And so we're able to pull out then what is it that Andrew Baker is talking about in this video. And certainly virtualization tools, comparing Docker with VirtualBox and VMware, that's what he's talking about there. And then over in the bottom of the left-hand side, take that and go back into Knowledge Graph and find out, okay, with respect to Docker, the subject of this video, and with respect to things like VirtualBox, what are the relationships between those? So we can go from a raw video segment and play these AI tricks and then link directly into a knowledge graph and find out really what is being talked about there. This doesn't always work. It works some, but the APIs from the vendors are still having problems. And I must say, I'm not a vendor. I'm using these technologies, and I'm looking at how the vendors are emerging. And what I can say is, this clip right here has 97% accuracy. Overall, if I take an average across that entire 3 hours of video, there might be 90, 91% average as far as how good is the transcript. And it's not even. There are many snippets that are really good, and we believe them. There are others, when they start to drop into like 80% confidence, we know that it's wrong. And the problem is largely that Google and others, on the one hand, they're not too eager to change their acoustic models. So if I have a speaker from Ohio and they're very clear, it's a good recording, I can get a pretty good transcript, as long as they're using words that are similar to what the models are trained on. When I get a speaker, in our case, a lot of our speakers have a very thick accent, whether they're from China or India or Russia or wherever. And so getting into a lot of accents is a big problem. And the vendors are really reluctant to change their acoustic models, although that may be changing. The other problem is that even though some of the vendors will allow you to give vocabularies, like here's a keyword list, that doesn't really work. To be able to do natural language understanding at an API level like this, you really need to provide more of a graph. You need to be able to give context in terms of, I know what the subject of this video is, I have a graph that shows the relationships between the topics that are expected, and if you don't have that kind of graph, you can't really do the tiebreakers when there's some ambiguous term. So the vendors are still struggling with whether or not they're going to allow acoustic models to change, whether or not they're going to accept graphs. We're working with them. I think the product managers are a little bit reluctant to really take in the kind of inputs they need from customers. But I'm hopeful that this is getting resolved. And so I've mentioned graph a few times. One of the things we've done is we have materials going back into, like 1978. And we front for more than 200 publishers. So we have all the books and videos for us and for Pearson, and there's Addison Wesleyan, there's all these other publishers involved. What we've been able to do then is to construct a graph to represent the kinds of topics that are in there and the relationships between them. So there may be Docker as a kind of software, but there's also Docker as a company, and then there's Kubernetes as a similar technology. And when you start to build out a graph like that, it gets really interesting. Number one, just as a way of having a kind of thesaurus to explain a domain. But number two, you can leverage the graph, you can compute it. And so we've been working on this, and we tie back into public resources. Library of Congress also has similar work, so we tie back into them. Library of Congress might know about neural networks, but they don't know much about deep learning.
Did you construct this graph manually, automatically?
That's a great question. So is the graph put together manually? And the answer is the core of it, the seed of it, yes. And so people have worked, and it's not easy work. It takes a long time, but we put together a core graph that has a few hundred relationships or main themes with some relationships. And then from there, we're able to use deep learning models, a process called vector embedding, where we can take that seed and add to it. So we can scan all the content from 200 different publishers, millions of chapters and segments, and see the relationships in the content, and then take that core and start adding to it where are the next big relationships that should be represented. So in that way, we are having both humans and machines working on it. And again, this is an area that even if you go directly to Google and Amazon and say, hey, I have a knowledge graph, how can I use it with your APIs? They're going to push back. They're starting to get there, but it's going to be a few more years. But when you do have text and you're working with or when you have video converted to text, let's say, and you're working with NLP, there's a lot of great things you can do with this. Obviously, finding key phrases is good. There's the notion that if you have a video and you want to look at where is it that this speaker has mentioned DevOps, let's say. So where do they make mention of specific concepts and related concepts, where in the video? Then you can do much smarter indexing into video products or audio products. I think that a lot of the big win for this is in summarization. Because once we have a transcript and we can parse a transcript and represent it as a graph, there's a way to be able to summarize it, collapse it down. I might be able to take a 45-minute talk and come out with a one-page summary. It's not perfect, but it's a lot better than having to watch 4,000 hours of video. And I think ultimately this leads to a lot better work with conversational interfaces. What we can do with understanding what's coming out of the text and what the context is going to have a lot of feedback into when we get into smaller conversations as well. So I do want to cover a little bit about NLP. And the thing is, there's been a big generational change in NLP, and I teach courses in NLP and AI, and I find that in industry, what's changed over the past 2-3 years isn't really well known. There's still a lot of concepts that are floating around that people take as givens that were outdated 10 years ago. So I definitely want to put in a plug. For one thing, a lot of people talk about NLP, and you might hear mentioned bag of words. I was recently at a research conference with PhD students, and they were mentioning this, and it was just amazing. This was an outmoded technique a long time ago. And so bag of words and other techniques like stemming and n-grams, and in general keyword search, like you'll see in Solar and Elastic and others, they were shortcuts because we didn't have enough computational power. And now we're seeing a lot better cloud resources and a lot better ways to work with NLP. So there's been a kind of generational lag, and even in the vendors, we're still seeing this. Even out of some of the Google APIs, they have some fairly old stuff that's hard-coded. Another notion that I find with NLP is that it really requires a lot of investment in big data frameworks, like you have to have a Spark cluster running or something like that. And again, that's no longer the case. I'll show that in a moment. But really the one that stands out to me is a kind of either-or fallacy that either you can fully automate a thing, or if you can't automate it, okay, we're not going to do that yet. What we're seeing is a lot of middle ground where problems can be partially automated and then have human in the loop, and the two of those together augment each other. Now, the thing that's really changed on this, as I mentioned, I was doing neural networks back in the 80s, and we didn't have enough hardware. And again, when we were doing NLP work on early social media, we ran into the problem of not really having enough hardware, but starting to get there. So what's changed is hardware is vastly different. If I take what was one of the largest Hadoop instances in the cloud from 2008, I can take that same algorithm and the same data, I can run it faster in Python on my laptop today. And it's only been 10 years. And so what we've seen is this real big change because of multi-core, because of having a lot of CPUs all in one chip. You don't need a huge cluster anymore. And also because of large memory spaces and faster interconnects, we can see a lot of workloads that would have required a big cluster before can all just be put on one machine. And there are projects like Apache Arrow that are really leveraging this in open source. I highly recommend. But hardware is changing. We're seeing not just CPUs. I think that for CPUs, Moore's Law and the advances we'd banked on for the last decades, that's all but dead. We're seeing a lot of advances now with GPUs. Anybody own NVIDIA stock? Anybody seen NVIDIA stock lately? It's been this hockey stick. GPUs are very popular. You can't buy enough of them these days. But even Google is moving beyond that. If you look at Jeff Dean's talk from NIPS in 2017, Google is moving away from GPUs. They've got TPUs that they've built. They have their second generation of them coming out now in use. They're working on their third generation. Google's essentially becoming a hardware vendor. And so they're building their own processors, and they're seeing substantial performance by doing custom work, creating hardware specifically for AI. We're also seeing IPUs, DWPUs, there's Cerebrus, doesn't have a name for their stuff yet, on and on. There's just this array of different work. Microsoft is leveraging FPGAs. A lot of interesting hardware is going on. And I had dinner last night with a friend who's a researcher in government here working on quantum control systems. Quantum computing is kind of a dangerous thing to mention. People roll their eyes. But I will say it's very real, and there's use cases coming out. So the hardware changes that we're seeing in the cloud right now are the thin edge of the wedge. A lot of the cloud providers are really gearing up for much more advanced hardware coming in over the next years. As well, we've had a lot of interesting advances with software in terms of like approximation algorithms, probabilistic data structures. They're a little bit more advanced on the math, but the bottom line there is we see much better ROI for using advanced math in hardware and low-level software. And that's something that wasn't true just a few years ago. So what this implies, here's a great quote from the AI evangelist out of Microsoft, quoting a Google talk. You know, Google has owned automated translation since 2005, the NIST challenge in 2005. But the code that they have to do that was getting up to like 5,000 lines of code. And it's a lot of special purpose classifiers and whatnot. And they went and replaced that with deep learning models using TensorFlow, and they dropped 500,000 lines of code down to 500 lines of code. 3 orders of magnitude increase in performance in terms of software. And while they did that, their translation quality jumped up by 30 points. And I'm quoting at the top here, a friend of mine went into Google a few years ago, Pete Warden, he's leading part of TensorFlow now. And although they're reluctant to speak too openly, this is from a blog post, they're seeing that kind of effect, orders of magnitude change in the software. They're seeing hundreds of projects every day have this kind of thing going on. And this is inside Google. Their prediction is that, you know, Pete's out there saying that within 10 years, software jobs won't involve programming. And I think he's wrong. I think it's more like 5 years. And it's not that software is going away, but writing code in an IDE is maybe interesting. If your kids are out learning Java, that's probably good. Please don't tell them to depend on having a job doing that. And when we look at code gen, especially human-in-the-loop code gen with AI, it's getting very commercial now. There are enterprise applications for that. Okay, so I hopefully did some not-so-scary things about where AI is going. I want to show some specifics. I'm going to brush through this because it's a little bit technical, but just to give you an idea about graphs. So there's a project called TextRank, and a friend of a friend, a close friend of mine, his research partner, Radha Mahasya, she came up with this algorithm and was subsequently hired by Google. The idea is that if you take a paragraph, or so, rather, let's start, if you take a text document and you split it into paragraphs and sentences, we have tools for that. Now, for each sentence, parse it with NLP. Every word, you know what the word is, you know what its root is, you know it's part of speech. You can now construct a graph. You can look at a noun and say, okay, what are its neighbors? Where are the adjectives? Where are the verbs? Where are the other nouns? And for the neighbors, link them together in a graph. And if you see repeat instances of the same root word, link those too. And if you have a knowledge graph, some context coming in, and you see links in common there, yeah, add those too. Now you end up with this graph representing your text document. And again, the text document may be a transcript from a video. So the trick in graph algorithms is we use this approach as something called centrality. Basically, we can look at all the parts that are linked together, and we can find out which are the ones that are the hubs, the ones that are most connected. And there are mathematical ways to describe that. One technique, it's something called eigenvalue centrality, a lot of 2-bit words. There's a variant of it called stochastic eigenvalue centrality. The other name for that is PageRank, so the algorithm that Google invented. Basically, once you've constructed a graph out of a text and you run PageRank on it, the most highly ranked phrases are the ones that have a lot of reference throughout the document. And so basically, you start pulling those out, and you come out with what we call a feature vector. You come out with a list of key phrases that are highly ranked, but they're also basically a characteristic of the document. And so this is a really great way not just to parse a text, but really start to understand what is that about. And it's a way to bring in prior knowledge. But an interesting thing, by the way, here's a GitHub. I'm one of the lead committers on this project that implements it in Python, open source on GitHub. One of the interesting things about this now is you can go back and reevaluate the text. If you've got that feature vector and the graph, you can go back and look at every sentence, and you can see what's the vector distance from a sentence to my feature vector. And now I can go through the entire document, and I'll rank those sentences, and then take the top n and put them back into their original order, and you come up with a summarization. This is a technique called extractive summarization. We use it for our search results, both on video and books. It works very well. Here's an example of taking an entire article and dropping it into a paragraph down in the bottom right. So, and there are ways of using deep learning with this too. Extractive summarization is one step. You can go a few steps further in terms of abstractive or generative summarization. But there are very interesting ways of using AI to take a large quantity of media and condense it down. And that's a big win if you're an editor and you have to watch 4,000 hours of video per year. You know, that's like 10 months of having your finger on the fast forward button. So summarization, I think, is a big upcoming tool and technique. I'm not going to go into this too much in lieu of the time, but let me get to active learning. So active learning is basically, I have a machine learning model that tries to predict what's the top key phrase, or what's the top annotation out of a text, let's say. I have a machine learning model. Semi-supervised machine learning means that you sometimes ask questions of humans. So in this case, if machine learning models can come back and make a prediction with a lot of confidence, great, use it, go with it, that's automated. If they don't have confidence, then you kick it back to the humans. The humans make a judgment, and that in turn helps to train the models further. Another way of saying this is think that you have a big piece of data that you have to label, have to categorize. You can use machine learning as a lens to sort of highlight which parts of it we think are good for training and which parts are most valuable to refer to a human expert, a domain expert. And so in this way, machine learning can leverage uncertainty and find out where are the most valuable parts of uncertainty and bring in the experts where they really matter. So it's becoming more of a management tool for how to combine machine learning with experts. I'm going to scoot through this in lieu of time, but we have a project based on Jupyter doing some of this in open source. And I'm happy to answer questions about it. I want to show, though, that there are a number of firms engaged in this, kind of a NASCAR slide. I've got some case studies in the slides if you look at them later. There's a free book free download called Active Learning. And it's about a company called Crowdflower that really pioneered a lot of this commercially about a decade ago. Anybody here a customer for Stitch Fix? They send out fashion boxes, subscription. One of my favorite startups, a friend of mine, Eric Colson, is chief algorithm officer there. And they're using this a lot. They have a lot of machine learning inside Stitch Fix to predict fashion for individuals. And then they use the machine learning models along with fashion experts. And they use this approach to be able to blend the two together. So again, human in the loop. Ernst & Young and other big consultants are using this now. There's a case study on lease accounting compliance. They were able to get 300% better consistency, 200% better efficiency by using human in the loop machine learning. And so we're seeing this in large enterprise cases. And a big thing about it is model interpretation. It's kind of a two-way street. You build up these complicated machine learning models by having human experts weigh in. You also want the experts to learn from what's accumulated in the models. And for other reasons, compliance and security and ethics, really, you want to be able to see what's going on inside the models and why. So I've tried to list some resources here. There's an open source project on GitHub called Skater that's really good for model interpretation. And this is a big part. And so I'll just throw this out here. Usually in big data, we think of putting together data products. We start with some different files. We do some joins. We do some transformations and some machine learning. And we end up with some data products at the end. It's a very linear way of doing a workflow. When we start to introduce human in the loop, we get into circularities. We get into feedback loops. And so this is a big change in the industry right now. A lot of the computing stacks, Spark and others, are very linear. But what we're looking at now is how do we leverage the feedback? And where do we include the people? Where do we leverage the automation? Active learning is a really good way to try to tie these two together. And we use it, again, like with transcriptions, for reducing the error rate on how transcriptions are parsed and classified. There's some interesting takeaways on this in terms of you've got groups of people with organizational learning, and you've got machine learning models, and you've got customer use cases. And between all of those, there are points of feedback where they're learning from each other. So I'm proposing this as kind of a better way to look at what's coming up with AI. And I think I've got some more slides, but we're coming out on time. The last thing I really want to point out, though, the guidance that we're seeing is not so much to build more faster, better, more intelligent machines. The guidance that we're seeing is leverage the intelligence that's already there. And so there's kind of an expectation that AI is going to come out of increasingly fancy programming, and it's BS. What we're seeing is you have to leverage the people. The intelligence in your organization is not inside your IT staff. The intelligence in your organization is in your customer support and your sales teams and your professional services. They're the ones who live with the customer, and they understand, they have the intelligence of the company. So finding ways to blend AI with the people who really know what's going on are very interesting. And I'm glad to see this used in media, but again, we're seeing it used in finance, we're seeing it used in intelligence work, a lot of different areas. I've got some other things here that I'll scoot through. I think I've probably made the point. I'll just leave you on that note. The future belongs to those who understand how to combine their unique experience with what algorithms do best. And with that, thank you very much. I think we have a few minutes for some questions or so. Is there any questions I could? Yes?
I was really interested in your description of the extractive summarization process and especially with media, multimedia input.
Yeah.
Can you talk about monitoring content on social media and how that sounds like a really good application for that capability?
Yeah, it's interesting because I think there's been so much. That area of monitoring social media has been tilted so much toward keyword analysis, and keyword is a really shallow way of looking at it. The other thing is sentiment detection. I work in NLP. I've worked in NLP for years. I've never believed sentiment detection. I've seen some of those algorithms from the inside, and it's just I would never make any bets on that. So I think that the tools that are out there for what's going on are a little iffy. On the other hand, in social media, maybe not so much the summarization side, although it comes in, but I've worked with a few people doing more analysis of what's going on in social media now, a lot of botnets and politically motivated botnets. So there's a large team called Data for Democracy, thousands of data scientists. And there's also another friend of mine related to that, Steve Kramer. Steve's an astrophysicist, and they do these really complex graph models when they look at galaxies colliding, right, through these huge telescopes. They've found ways to apply the same math for social media and to be able to piece out where are the botnets and where are the real people. And so I think if you look at some of Steve Kramer's work on astrophysics applied to Russian botnets, there's some really interesting things that pop out. Lately, they've been publishing in real time while attacks are happening. I think that summarization can be used in social media, particularly if you've got more text. If you're just working with tweets, it's pretty thin. Does that help?
I guess what I was thinking of, I've heard that YouTube is hiring hundreds and hundreds of humans to watch
Yeah.
videos and make sure there isn't anything inappropriate.
Yeah.
And I think we have technology to do a lot of that. So I was wondering what's going on there, if you have any ideas.
I see what you mean. That's a really good point. I mean, yeah, I'll repeat the question there. So we were talking about summarization and some of these technologies for natural language understanding with respect to what's going on in social media right now. And when we talk about social media, we may think of tweets and doing sentiment analysis on tweets. I'm going to put it in a bucket over there. A lot of the bigger problem is when you get into video, as we were talking about on YouTube. How can you really understand the content that's inside the video? Because it's subtle. And there are social hacks to try to make it even more subtle. So this is coming into effect. We can definitely do a lot more work with understanding what's going on in a video. I think that when we get into social media like YouTube and others, they're going to look at the cost basis. because it is expensive. And the thing that I find with the incumbents, the flywheel effect that I mentioned, there's the companies like Google, Amazon, Apple, Baidu, Microsoft. All of them have the same characteristics where they own a cloud, they have amazing AI teams, and they have some kind of mobile or embedded products where they generate a lot of data. And so they use those three things together. And they've been really successful at it, and they're going to continue to be successful, and they're blocking other companies. But the thing that I find that's kind of their Achilles heel is they tend to go toward the full automation side. If something can't be fully automated, they don't want to touch it because it incurs too much human expense, and that's antithetical for them. So that's actually opening the door for people to compete with some of these majors is, even though you may not hire all the top PhDs, if you can get that human expertise in the loop, you may be able to come out with a better product. And I think that that's kind of YouTube's undoing currently, as I'm reading in the media. And I certainly see that across the board with Google and Amazon, where they could be doing much better, they have the technology, it's a matter of cost and how they regard automation versus people. Was that a good question? Other questions? I'm coming up on time, so I'll be around. I'd love to talk, and I look forward to conversations later in the day. Thank you very much.